Picture this: a swirling tempest so vast it could swallow Earth whole. A storm that has raged for centuries in the thick, turbulent atmosphere of Jupiter. Now imagine that storm, the Great Red Spot, shifting its shape dramatically in just a matter of hours. Not over years, not over decades, but overnight. This isn't some fantastical tale from the edges of science fiction. It's a real, jaw-dropping event that unfolded right before the eyes of astronomers, leaving them scrambling for answers. What could possibly cause such a colossal storm, one of the most enduring features in our solar system, to transform so suddenly? And why, of all things, did its new shape eerily mirror a pattern we've seen on our own sun? Jupiter has always been a planet of extremes, a gas giant so massive it bends the rules of physics, a world where storms rage with unimaginable fury, and where mysteries lurk beneath layers of swirling clouds. But this particular event, this overnight transformation, stands out as one of the most puzzling and electrifying discoveries in recent planetary science. It's a reminder that even after centuries of observation, our solar system still holds secrets capable of rewriting what we thought we knew. The Great Red Spot, that iconic crimson whirlwind, isn't just a static feature. It's alive, dynamic, and far more unpredictable than anyone ever imagined. So what does it mean when a storm that's existed longer than modern astronomy suddenly decides to reinvent itself? Could this be a clue to Jupiter's deeper workings, a hint at hidden forces shaping its atmosphere? Or is there something even more profound at play, a connection between the turbulent skies of Jupiter and the swirling plasma of our Sun? Today, we're diving deep into the heart of this cosmic enigma, unraveling the science behind the storm, the theories that attempt to explain its sudden shift, and the breathtaking implications for our understanding of not just Jupiter, but the very nature of planetary weather across the universe. Strap in, this is one journey you won't want to miss. For centuries, the Great Red Spot has dominated Jupiter's atmosphere like a fiery pinwheel spinning endlessly in the void. First spotted by astronomers in the 1600s, this monstrous storm could swallow our entire planet with room to spare. Imagine winds screaming at over 400 miles per hour, swirling in a chaotic dance that's outlasted empires, revolutions, and humanity's entire exploration of space. Yet for all its permanence, this storm is anything but static. Recent observations revealed something astonishing, a sudden, dramatic shift in its shape, as if the storm itself decided to reinvent its identity overnight. What keeps this ancient tempest churning? Unlike Earth's hurricanes, which fade when they lose energy from warm ocean waters, Jupiter's Great Red Spot is a self-sustaining beast. With no solid surface to slow it down, the storm feeds off the planet's own turbulent atmosphere, drawing power from jet streams and mysterious heat rising from deep below. Scientists believe its iconic crimson hue comes from chemicals like ammonia and sulfur, cooked by ultraviolet light into complex compounds we're still trying to understand. But the real puzzle isn't just its longevity, it's the way it behaves. The storm shrinks, grows, and even changes color over time, like a living thing responding to its environment. Then came that baffling night when telescopes caught the spot twisting into a new form, its edges stretching and contorting as if pulled by invisible hands. Even more startling, the reshaped storm bore an uncanny resemblance to solar flares, those snaking tendrils of plasma we see erupting from the sun's surface. Could there be a hidden connection between Jupiter's storms and our star's explosive activity? Some researchers think swirling magnetic fields or charged particles might be at play, linking two seemingly unrelated phenomena across the vastness of space. This isn't just about a storm changing shape, it's a clue to the hidden forces shaping gas giants. By studying the Great Red Spot's sudden transformation, we're peering into the engine room of Jupiter's weather system, where winds scream faster than bullets and storms last longer than civilizations. Every twist, every shift whispers secrets about how planetary atmospheres evolve, not just in our solar system, but around distant stars. The Great Red Spot isn't merely a spectacle, it's a cosmic laboratory, and its latest act has left scientists with more questions than answers. In 2019, something extraordinary happened. A storm older than modern science itself began rewriting the rules before our eyes. The Great Red Spot, Jupiter's signature tempest, had always been a model of consistency, its oval form spinning like a perfect, if violent, top. Then, almost without warning, it started to unravel. High above Earth, the Hubble Space Telescope captured images that left astronomers speechless, fragments of the storm peeling away like petals in a cosmic wind, its edges jagged and uneven. This wasn't the slow, gradual change scientists had come to expect. This was a planetary-scale metamorphosis playing out in hours, not centuries. What could rip apart a storm wider than our planet? One theory points to violent clashes deep within Jupiter's atmosphere. Imagine two colossal jet streams, rivers of gas moving at different speeds, suddenly tangling like dueling snakes. The friction alone could shred the edges of even the mightiest storm. Others suggest the answer lies in chaos bubbling up from below, mysterious heat surges rising from Jupiter's hidden depths, destabilizing the spot's delicate balance. But the most tantalizing clue came when researchers noticed the storm's new shape bore a striking resemblance to something far more familiar, the fractal-like tendrils of a solar flare. Could Jupiter's atmosphere, with its swirling metallic hydrogen and titanic magnetic fields, be mimicking the same physics that govern our Sun? This wasn't just a storm changing, it was a window into forces we're only beginning to comprehend. On Earth, storms fade when they lose energy. Jupiter's storms seem to feed off chaos itself. The Great Red Spot's sudden transformation challenges everything we thought we knew about planetary weather, suggesting that gas giants operate by a playbook we've barely opened. Every twisted filament, every broken fragment in those Hubble images is a piece of a puzzle that could rewrite textbooks, and the most thrilling part. This might not be a one-time event. If Jupiter's atmosphere is this dynamic, what other surprises are lurking in its clouds, waiting to upend our understanding of the cosmos? The resemblance was impossible to ignore. Those jagged, twisting filaments at the edge of Jupiter's transformed storm looked like they'd been plucked straight from the surface of our Sun. Solar flares, those explosive arcs of plasma that snake outward from sunspots, share an eerie visual kinship with the Great Red Spot's new configuration. It's a comparison that sent shockwaves through the planetary science community, because if these two phenomena are connected, it would mean Jupiter's atmosphere operates by rules we've only ever associated with stars. So how could a planetary storm mimic the behavior of our Sun? One compelling theory points to magnetism. Jupiter boasts the strongest magnetic field of any planet in our solar system, a turbulent force field generated by churning metallic hydrogen deep in its core. This magnetism doesn't just create dazzling auroras, it shapes the very storms raging in the atmosphere above. Charged particles, whipped into frenzy by the planet's rotation, could be threading through the Great Red Spot like invisible wires, forcing its gases into patterns that mirror solar flares. It's as if Jupiter's atmosphere is conducting electricity on a planetary scale, with the storm acting like a cosmic fingerprint of those hidden forces. Then there's the role of shear, the violent tug of war between different layers of Jupiter's atmosphere. Just as the Sun's plasma twists and snaps under competing magnetic pressures, Jupiter's jet streams might be shredding the edges of the Great Red Spot into those familiar fractal-like tendrils. Recent computer simulations suggest that when these supersonic winds collide, they create instabilities nearly identical to those seen in solar prominences. The physics isn't just similar. In some cases, the equations used to model solar weather can be directly applied to Jupiter's storms. But perhaps the most tantalizing clue comes from chemistry. Solar flares glow because superheated plasma emits light. Could something analogous be happening in Jupiter's clouds? The spot's crimson color has long been a mystery, but some lab experiments show that sulfur compounds, when zapped with ultraviolet light or electrical currents, can produce similar hues. If Jupiter's storm is essentially a planetary-scale plasma discharge, it would explain both the color and the uncanny solar resemblance. This isn't just about solving a puzzle on Jupiter, it's about rewriting how we classify cosmic weather. For decades, scientists treated planetary atmospheres and stellar activity as separate disciplines. Now, the Great Red Spot is blurring those boundaries, suggesting the same fundamental processes might govern storms across the universe, whether in the clouds of a gas giant or the furnace of a star. Every time this ancient storm surprises us, it's not just changing shape, it's changing our understanding of the forces that shape worlds. Jupiter's atmosphere isn't just chaotic, it's a roiling, churning laboratory of extreme physics unlike anything we experience on Earth. Picture an ocean of hydrogen and helium so deep it defies comprehension, where the very air we'd call sky transforms under crushing pressures into exotic metallic forms. This isn't weather as we know it. It's a continuous explosion of energy where winds reach speeds that would strip the flesh from bones, where storms don't fade but persist for centuries, feeding off the planet's own furious rotation. At the heart of this maelstrom sits the Great Red Spot, not as an outsider but as a product of its environment, a monstrous child birthed and sustained by Jupiter's endless atmospheric tantrums. What makes this gas giant's weather so violently different? Start with the basics. Earth storms draw energy from sunlight warming our oceans, but Jupiter generates its own heat from within, radiating nearly twice the energy it receives from the sun. This internal furnace sets the stage for constant upheaval, where convection currents rise like boiling water in a pot the size of a planet. Then there's the Coriolis effect, the same force that twists our hurricanes, amplified to nightmare proportions by Jupiter's 10-hour day. A planet spins so fast it stretches weather systems into bands of eastward and westward jet streams, some moving over 300 miles per hour faster than their neighbors. When these atmospheric rivers collide, they don't just create eddies, they spawn storms that could swallow continents whole. The Great Red Spot thrives in this pandemonium like a shark in chummed waters. Nestled between two especially violent jet streams, it's essentially a spinning wedge of stable chaos, a hurricane that's found the perfect balance between competing forces. But stability here doesn't mean stillness. Recent data from NASA's Juno spacecraft reveals titanic plumes of ammonia rising from depths over 200 miles below the visible cloud tops, delivering fresh fuel to the storm like oxygen to a fire. These vertical currents may explain why the spot occasionally darkens or brightens, its chemistry altered by injections of material from Jupiter's hidden depths. Yet this delicate equilibrium can shatter without warning, when particularly energetic disturbances ripple through Jupiter's atmosphere, perhaps triggered by collisions with asteroids too small to detect or by internal pressure shifts we don't yet understand. The Great Red Spot structure wobbles like a top losing momentum. That's when we see those bizarre transformations, filaments stretching outward, the storm's edges fraying like wet paper under tension. These moments reveal the spot's true nature, not as a solitary phenomenon, but as a knot in Jupiter's atmospheric fabric, constantly rewoven by forces far beyond our current understanding. The most fascinating part, we might be looking at a universal recipe. Similar banded patterns appear on Saturn, and even distant exoplanets show signs of jet stream-driven weather. Jupiter's atmosphere could be showing us how all gas giants behave, a masterclass in planetary fluid dynamics written in clouds of ammonia and hydrogen. Every time the great red spot twitches or transforms, it's not just changing itself, it's sending us coded messages about how energy flows through alien skies, messages we're only beginning to decipher. Wind shear is the invisible sculptor of Jupiter's storms, an atmospheric force so powerful it can twist a centuries-old tempest into new shapes overnight. Imagine two colossal rivers of gas, one racing eastward at 300 miles per hour, another sliding westward just above it, slower but no less relentless. Where these layers grind against each other, the friction doesn't just create turbulence, it warps storms like clay on a potter's wheel. This is what scientists believe happened to the Great Red Spot when Hubble captured its sudden transformation. Wind shear, acting like cosmic scissors, snipping and reshaping the storm's edges into those eerie, solar flare-like tendrils. But wind shear doesn't just alter storms, it determines whether they live or die. Smaller storms on Jupiter face a brutal fate. If wind shear rips them apart before they can anchor themselves between jet streams, they vanish like smoke in a hurricane. Others, caught in just the right balance of forces, merge into larger systems, feeding off each other's energy. It's a celestial Darwinism, where only the storms that adapt to the planet's ferocious wind patterns survive. The Great Red Spot, it's the ultimate survivor, a storm that's mastered the art of riding these atmospheric currents like a surfer on a never-ending wave. What makes Jupiter's wind shear so extreme? The planet's lack of a solid surface means there's nothing to slow down its churning atmosphere. Earth's mountains and oceans act like brakes on our weather systems, but Jupiter's winds scream unimpeded around the globe, stacking into layers that move independently at dizzying speeds. Data from the Juno spacecraft reveals these layers extend hundreds of miles deep, with shear forces magnified by the planet's own internal heat. When these stratified winds collide, they don't just nudge storms, they rewrite them. The real breakthrough came when researchers noticed something startling. The same physics governing Jupiter's wind shear applies to Earth's hurricanes. Our most destructive storms weaken when upper-level winds tear them apart, a milder version of what happens daily on Jupiter. This cosmic parallel suggests that wind shear isn't just a quirk of one planet. It's a universal architect of weather, from the smallest thunderhead to galaxy-sized tempests on distant gas giants. Now, scientists are racing to decode the hidden language of these wind patterns. Every twist in the Great Red Spot, every merger of smaller storms, is a clue to predicting how Jupiter's atmosphere might evolve next. Some models suggest the spot could eventually fragment if shear forces overwhelm it, while others propose it might absorb neighboring storms to grow even larger. One thing's certain, Jupiter's winds are the conductors of this chaotic symphony, and we're only beginning to hear the music. Jupiter's magnetic field isn't just strong, it's a monster, a swirling, invisible force 20,000 times more powerful than Earth's. This planetary-scale dynamo, generated by churning metallic hydrogen deep within the planet's core, doesn't just create dazzling auroras. It might be the hidden hand shaping the very storms we see raging in its atmosphere. Imagine an invisible web of magnetic lines stretching hundreds of thousands of miles into space, tangling with the charged particles in Jupiter's clouds. Some researchers believe this electromagnetic dance could be the secret behind the Great Red Spot's astonishing longevity, a storm that refuses to die even as smaller tempests flicker out around it. Here's how it might work. As Jupiter's furious winds whip ammonia and water vapor through the atmosphere, these molecules collide, stripping electrons and creating a soup of charged particles. This ionized gas or plasma becomes ensnared in the planet's magnetic grip, effectively turning the storm into a colossal electrical circuit. Magnetic forces could act like an invisible scaffold, preventing the spot from dissipating even as it's battered by sheer winds. It's as if the storm has an electromagnetic skeleton, one that's kept it standing for centuries while other weather systems crumble. But what happens when that magnetic field flickers? Jupiter's magnetism isn't perfectly stable. Data from the Juno spacecraft reveals sudden spikes and dips in intensity, like a power grid surging during a storm. These fluctuations might explain why the Great Red Spot shape can warp so dramatically overnight. If the magnetic scaffolding weakens even briefly, the storm's structure could twist under atmospheric pressures, morphing into those bizarre solar flare-like tendrils. Alternatively, a surge in magnetic energy might inject fresh chaos into the storm's heart, stirring it into new configurations. The most compelling evidence comes from the spot's darker moments. Observations show its color deepens when magnetic activity spikes, as if some unseen force is charging the storm's chemistry. Lab experiments back this up. When ammonia and sulfur compounds are zapped with electrical currents, they darken to a richer red, mirroring the spot's behavior. This suggests the storm isn't just shaped by magnetism. It might be glowing because of it, a planetary-scale neon sign powered by Jupiter's internal dynamo. Yet mysteries remain. Why does the spot sometimes resist these magnetic tugs, holding its shape for decades, only to suddenly unravel? Some theories point to deeper, unseen layers of the atmosphere, where rivers of liquid metallic hydrogen could be generating secondary magnetic fields, creating a chaotic interplay of forces. Others speculate that impacts from asteroids or comets too small for us to detect from Earth might send shockwaves through Jupiter's magnetosphere, briefly destabilizing the storm. One thing's clear: Jupiter's storms don't play by Earth's rules. Our hurricanes fade when they lose heat energy, but the Great Red Spot might draw power from the planet's magnetism itself, turning atmospheric chaos into a self-sustaining engine. If true, this would rewrite how we understand weather on gas giants, not as passive systems driven by sunlight, but as dynamic, electromagnetically charged phenomena. The next time the spot twists into a new shape, it might not just be responding to the wind, but to the invisible pulse of Jupiter's beating magnetic heart. Think of Earth's mightiest hurricane, a swirling beast of wind and rain that churns across the ocean for weeks, leaving devastation in its wake. Now picture that same storm, but instead of fizzling out over cold water, it keeps raging, not for months but for centuries. This is the staggering reality of Jupiter's storms, where the rules of weather defy everything we know about our own planet. At first glance, the physics seem familiar. Both Earth's hurricanes and Jupiter's vortices thrive on heat, spin from planetary rotation, and feed off pressure differences. But the differences, they're cosmic. Earth's hurricanes are like candles in the wind, bright, intense, but ultimately fleeting. They draw energy from warm ocean waters, and the moment they hit land or cooler seas, they sputter out. Jupiter's storms, by contrast, are more like wildfires in an endless forest. With no solid surface to disrupt them, they feed off the planet's own internal heat, a furnace so intense it radiates more energy than Jupiter receives from the sun. Imagine a hurricane that never runs out of warm water, and you'll start to grasp why the Great Red Spot has outlasted civilizations, rotation plays a starring role too. Earth's 24-hour day gives our storms a gentle nudge, shaping them into spirals. Jupiter's 10-hour spin is a different beast entirely. It whips the atmosphere into a frenzy, stretching storms into bands and ovals like taffy pulled at supersonic speeds. This extreme rotation doesn't just sustain storms, it locks them into stable configurations, turning temporary disturbances into permanent fixtures. Then there's the matter of scale. A Category 5 hurricane might span 400 miles, terrifying for us, but a speck compared to Jupiter's Great Red Spot, which could swallow Earth whole. Size matters here. Larger storms lose energy more slowly, like a massive flywheel that keeps turning long after the initial push. But perhaps the most striking difference lies in what happens at the edges. On Earth, friction with land or cooler oceans drains a storm's energy. On Jupiter, storms don't dissipate, they collide. Smaller vortices merge like droplets of mercury, feeding larger systems in an endless cycle of atmospheric cannibalism. Yet for all their differences, studying Jupiter's storms shines a light back on our own world. The same fluid dynamics that govern Earth's weather apply there, just amplified to extremes. By understanding how storms behave in Jupiter's alien environment, we're uncovering universal truths about how turbulence works, how energy flows, and how chaos can sometimes give birth to eerie stability. It's a reminder that the laws of physics are written across the cosmos, whether in the fleeting fury of an earthly hurricane or the ageless rage of a storm that's outlasted telescopes, civilizations, and perhaps even the stars it formed beside. Most storms in our solar system flare up and fade like sparks in the wind except one. The Great Red Spot isn't just surviving, it's thriving, a tempest that's endured while countless others have vanished into Jupiter's chaotic skies. So what's its secret? Why does this ancient storm refuse to die when even the mightiest hurricanes on Earth sputter out after weeks? The answer might lie in the very fabric of Jupiter's alien atmosphere, where the rules of meteorology are rewritten at every turn. Start with the storm's food source. On Earth, hurricanes guzzle warm ocean water like fuel, collapsing when they hit land or cooler seas. But Jupiter has no oceans, no continents, just an endless, churning abyss of gas. Here, the Great Red Spot feeds on something far more potent, the planet's own internal heat. Deep beneath those swirling clouds, temperatures soar to thousands of degrees, heated by the slow collapse of Jupiter's core and the crushing weight of its atmosphere. This heat doesn't just warm the air, it sets the entire atmosphere boiling, creating updrafts powerful enough to sustain storms for centuries. Imagine a hurricane perched over an eternal volcano, constantly bathed in rising energy. That's the spot's first survival trick. Then there's the storm's predatory nature. Jupiter's skies are a battlefield where smaller vortices collide, merge, and are devoured. The Great Red Spot isn't just a passive observer, it's an apex predator. Observations show it cannibalizing smaller storms, absorbing their energy like a cosmic vampire. In 2018, astronomers watched as a swirling filament of gas, itself larger than Earth, spiraled into the spot's outer winds. Instead of weakening the storm, this merger left it reinvigorated, its colors deepening as if fed by some celestial transfusion. It's a brutal but effective strategy. In a world where size equals longevity, the spot grows by consuming its rivals, but the real enigma lies deeper. Recent data from NASA Juno spacecraft reveals something startling. The storm might be tapping into hidden reservoirs of energy far below Jupiter's cloud tops. Microwave scans show plumes of ammonia and water vapor rising from depths exceeding 200 miles, punching through layers of atmospheric sludge to deliver fresh fuel to the spot's core. These storm routes suggest the Great Red Spot isn't just a surface phenomenon. It's a sprawling weather system with tendrils anchored in Jupiter's unseen depths. Picture a tree drawing water from underground aquifers, except here, the tree is a storm and the water is a river of superheated, electrically charged gas. The most radical theory, the storm might be generating its own energy. Some researchers speculate that the spot's rotation, combined with Jupiter's monstrous magnetic field, could be turning it into a planetary-scale dynamo. Charged particles swirling within the storm might create electrical currents, effectively making the spot a self-sustaining engine. It's a wild idea, a storm that powers itself like a perpetual motion machine, but lab experiments show that ionized gases under extreme pressure can exhibit eerily similar behavior. If true, the Great Red Spot isn't just enduring, it's engineering its own survival. Yet for all these theories, the storm's longevity remains one of planetary science's greatest puzzles. Every explanation fits pieces of the puzzle, but none complete the picture. What we do know is this: the Great Red Spot isn't just a relic of the past. It's a living laboratory, a window into the extreme physics governing gas giants across the universe. And as long as it keeps churning, it'll keep challenging everything we thought we knew about the life and death of storms. NASA Juno spacecraft slipped into Jupiter's orbit in 2016, and since then, it's been rewriting the textbooks. This isn't your average planetary probe. It's a high-tech detective, armed with instruments designed to peel back Jupiter's swirling clouds and expose the secrets beneath. While telescopes on Earth can only glimpse the surface, Juno dives deep, measuring magnetic fields, mapping temperatures, and even sniffing out the chemical makeup of storms like the Great Red Spot. What it's found is nothing short of revolutionary. A world where storms aren't just skin-deep but plunge hundreds of miles into the planet's interior, where the very fabric of weather defies our understanding. One of Juno's most startling discoveries lies beneath the Great Red Spot itself. Using microwave technology, the spacecraft revealed a hidden structure, a storm route extending over 200 miles downward, far deeper than anyone predicted. This isn't just a surface whirlwind. It's a colossal atmospheric chimney, funneling heat and gases from Jupiter's scorching depths into the storm above. Think of it like a planetary-scale geyser, but instead of water, it's blasting ammonia and organic compounds into the maelstrom, constantly feeding the spot's fury. This could explain why the storm has endured for centuries. It's not just drawing energy from the surrounding winds, but tapping into reserves far below. Then there's the magnetism. Juno's magnetometer has mapped Jupiter's magnetic field in unprecedented detail, uncovering chaotic patches where the field flips polarity like a malfunctioning compass. These anomalies seem to align eerily with the Great Red Spot's location, hinting at a direct link between the storm and the planet's invisible magnetic forces. Some scientists now suspect the spot might be acting like a giant conductor, its swirling gases generating electrical currents that interact with Jupiter's magnetosphere. If true, this would make the storm not just a weather phenomenon but an active player in the planet's electromagnetic drama. Juno's cameras have also captured something unexpected. The spot's color changes aren't random. When the storm darkens to a deep crimson, Juno detects spikes in ultraviolet radiation hitting its upper clouds. This suggests sunlight might be cooking chemicals in the storm's gases, altering their hue like a cosmic mood ring. But here's the twist. These color shifts often coincide with fluctuations in the magnetic field, implying that Jupiter's invisible forces might be pulling the strings on the storm's appearance. Perhaps most tantalizing are Juno's gravity measurements, which reveal how mass is distributed beneath Jupiter's clouds. The data shows the Great Red Spot isn't just a swirling patch. It has weight, a detectable gravitational signature that distorts the planet's field. This means the storm isn't just a thin layer of angry gas. It's a massive, dense structure, something more akin to a solid object floating in the atmosphere. Yet for all these breakthroughs, Juno has also deepened the mystery. The spacecraft watched as the spot's transformation unfolded in real time, capturing the moment its edges frayed into those solar flare-like filaments. What it saw defied expectations. The storm wasn't just being torn apart by wind shear, it seemed to be reorganizing itself, like a living creature adapting to new conditions. Some researchers now wonder if Jupiter's storms follow a kind of cosmic evolution, where only the most efficient structures survive. Juno's mission was supposed to answer questions, and it has, but like all great explorers, it's uncovered far more than anyone anticipated. Every orbit, every scan peels back another layer of Jupiter's enigma, revealing a world where storms are deeper, weirder, and more interconnected than we ever dreamed. And with the spacecraft still circling, who knows what other secrets the Great Red Spot and Jupiter itself might still be hiding. Infrared telescopes have peeled back Jupiter's thick cloud layers to reveal something invisible to the naked eye, the scorching and freezing heartbeats of its storms. While the Great Red Spot might look like a smooth, swirling disk in visible light, infrared observations paint a far more chaotic picture. Thermal imaging uncovers a storm seething with temperature extremes, where some regions glow white-hot while others plunge into frigid darkness. These aren't just random fluctuations, they're vital clues to why this centuries-old tempest keeps reinventing itself overnight. At the storm's edges, infrared cameras detect something startling: tendrils of warmer gas snaking outward, like fingers reaching into Jupiter's colder atmosphere. These thermal filaments match exactly where Hubble saw the storm's shape distorting, suggesting heat is the invisible sculptor behind those sudden transformations. Warmer regions rise like bubbles in boiling water, stretching and twisting the spot's outer layers, while cooler sinks act like anchors, pulling sections inward. It's a constant tug of war between expansion and contraction, with temperature calling the shots. But the real surprise lies at the storm's core. While most hurricanes on Earth have cold centers, the Great Red Spot defies expectations. Its heart isn't uniformly chilly. Instead, infrared scans reveal a patchwork of hotspots, some reaching temperatures dozens of degrees warmer than their surroundings. These fiery pockets might be the engine keeping the storm alive, pumping energy upward like subterranean vents fueling a volcano. Some researchers think these heat anomalies come from deeper layers, where Jupiter's internal furnace forces gases to rise violently through the storm's base. Others speculate they're caused by chemical reactions, as ammonia and sulfur compounds collide under extreme pressure, releasing bursts of thermal energy. Then there's the storm's eerie cold zones. In certain areas, temperatures plummet so drastically that infrared telescopes see them as in-sky voids. These frigid patches might be where the spot's rotation flings gas outward, creating low-pressure chimneys that suck heat away. Or they could mark the boundaries where the storm shears against Jupiter's jet streams, like two grinding ice sheets generating a cosmic cold front. What's fascinating is how these thermal extremes interact. Hotspots might destabilize the storm's structure, while cold zones reinforce it, creating a delicate balance that tips whenever the storm morphs. The most tantalizing data comes from comparing infrared maps over time. On nights when the Great Red Spot suddenly stretches or contorts, its heat signature shifts first, as if the temperature changes are pulling the strings. Sometimes a cluster of hotspots will ignite near the storm's edge hours before filaments begin peeling away. Other times, a cold core will intensify right before the spot's shape tightens into a perfect oval. It's almost as if the storm telegraphs its next move through thermal whispers. If only we knew how to read them. these observations aren't just about Jupiter. The same infrared techniques are now being used to study storms on Saturn, Neptune, and even distant exoplanets. Every temperature map of the Great Red Spot is a Rosetta Stone for decoding weather across the cosmos, proof that hidden beneath the chaos of swirling clouds, there's a universal language of heat, motion, and energy waiting to be translated. And with each new infrared scan, we're learning to listen. To understand a storm that defies centuries of expectations, scientists have turned to the digital realm, building virtual Jupiters inside some of the world's most powerful supercomputers. These aren't just animations, they're mathematical mirrors of reality, where every equation represents a law of physics playing out in the gas giant's turbulent skies. One simulation at NASA Ames Research Center required over 5,000 computing cores working in concert, crunching numbers for months to recreate just a few weeks of the Great Red Spot's life. The results, a digital storm that breathes, pulses, and morphs in ways eerily similar to its real-world counterpart, complete with those baffling overnight transformations. What makes these simulations so groundbreaking is their ability to isolate variables no telescope can see. Want to test if Jupiter's magnetic field caused the spot's sudden shape change? Remove the magnetism in the model and watch what happens. Curious whether a hidden heat surge destabilized the storm. Inject virtual thermal energy deep below the clouds and track the ripple effects. It's like having a cosmic control panel where scientists can tweak Jupiter's atmosphere one knob at a time. Recent simulations from Japan's Riken Institute revealed something startling when wind shear parameters matched data from Juno's flybys. The virtual spot spontaneously sprouted filaments nearly identical to those Hubble photographed. Not over centuries, not over years, but in mere simulated hours. Yet the real magic happens when simulations collide with reality. In 2021, a team at the University of California, Berkeley predicted that the Great Red Spot's next shape shift would coincide with a surge in nearby jet stream velocities. 6 months later, Hubble confirmed it. The storm's edges frayed exactly when and where the models said they would. This wasn't just a lucky guess. It was proof that the physics encoded in these simulations mirrors Jupiter's actual atmospheric machinery. But simulations also spotlight how much we still don't know. Some models suggest the spot should have dissolved decades ago based on classic fluid dynamics. Others show it stabilizing when fed by hypothetical energy sources from Jupiter's depths, sources we've yet to directly observe. This gap between prediction and reality isn't a failure. It's a treasure map highlighting where our understanding of planetary weather might be missing entire chapters. Perhaps most exciting is how these digital experiments bridge scales. The same simulations that model Jupiter's global winds can zoom in to track individual ammonia crystals swirling inside the spot's heart, revealing how microscopic processes might govern a storm wider than planets. It's a reminder that the Great Red Spot isn't just a spectacle, it's a classroom, teaching us how chaos and order dance across the universe, from Jupiter's clouds to the atmospheres of exoplanets we've yet to name. And with every processor cycle, we're getting closer to speaking the storm's ancient, turbulent language. When the Great Red Spot twisted into its strange new shape, scientists scrambled to explain how a storm that had maintained its structure for centuries could rewrite the rules overnight. One leading theory suggests a violent encounter with another storm, Jupiter's version of a cosmic fender bender. Imagine two hurricanes colliding over the Atlantic, but scaled up to planetary proportions. Smaller vortices constantly churn through Jupiter's cloud belts, and if one plowed into the spot's outer edges, the impact could send ripples through its structure. Infrared observations lend some credence to this idea just before the transformation. telescopes detected an unusually warm patch near the spot's perimeter, possibly the thermal fingerprint of a collision. But there's a catch. The sheer size of the Great Red Spot means any storm capable of noticeably altering it would need to be nearly as large, raising questions about how such a titanic clash could go unnoticed until after the fact. Another camp argues the change came from within. The spot isn't a solid object but a swirling fluid, vulnerable to instabilities that can cascade without warning. Picture a whirlpool in a bathtub seemingly stable until a slight change in water flow suddenly distorts its shape. On Jupiter, these instabilities might be triggered by surges of heat from below or shifts in the ammonia-rich currents feeding the storm. Computer simulations show that when certain velocity thresholds are crossed in the spot's internal winds, its outer layers can peel away like an onion unraveling. This could explain why the transformation appeared so abrupt. What looked like an overnight event might have been the culmination of invisible pressures building for months beneath the cloud tops. Then there's the atmospheric wave theory. Jupiter's skies are crisscrossed by massive undulations, think of ocean waves, but made of gas and stretching thousands of miles across. These waves typically propagate harmlessly, but under the right conditions, they can transfer energy into storms like the Great Red Spot. If a particularly powerful wave train slammed into the storm at a resonant frequency, it could have excited the spot's outer regions, forcing them to oscillate until they snapped into a new configuration. Some researchers point to the timing of the shape shift. It coincided with a period of heightened wave activity observed by NASA's Juno spacecraft, adding circumstantial evidence to this explanation. But the most tantalizing possibility ties all three theories together. Perhaps the spot's transformation wasn't caused by one event but a chain reaction, a smaller storm collision that weakened the spot's outer edges, making it susceptible to internal instabilities, which were then amplified by passing atmospheric waves. This cocktail of influences might explain why the event was both sudden and rare, requiring a perfect storm of conditions to trigger such a dramatic change. What's clear is that no single theory fully accounts for every observed detail, leaving scientists with a puzzle as layered as Jupiter's atmosphere itself. Each explanation shines light on different facets of the phenomenon, revealing just how complex and interconnected the planet's weather systems truly are. The Great Red Spot shape shift isn't just a curiosity, it's a masterclass in how even the most seemingly stable features in our solar system are governed by forces we're only beginning to comprehend. The solar wind isn't just a gentle breeze from the sun, it's a hurricane of charged particles racing through space at nearly 1 million miles per hour, and Jupiter stands directly in its path. This relentless barrage shapes the gas giant's magnetosphere, stretching it into a teardrop that trails billions of miles behind the planet. But what if this cosmic wind does more than just sculpt magnetic fields? What if it's the invisible hand that tweaked the Great Red Spot shape overnight? The timing is suspicious. Just before Hubble spotted the storm's transformation, solar observatories recorded a spike in solar wind intensity, a surge so powerful it compressed Jupiter's magnetosphere to half its usual size. Think of it like a sudden gale hitting a spinning top. The added pressure could have jostled the delicate balance keeping the spot stable. Charged particles flooding into Jupiter's upper atmosphere might have altered electrical currents feeding the storm, or even triggered chemical reactions that destabilized its structure. It's not as far-fetched as it sounds. We've seen solar wind stir up auroras on Jupiter brighter than entire planets, proof that the sun's influence reaches far beyond light and heat. Yet the solar wind theory isn't without its critics. Jupiter's magnetic field is a fortress, deflecting most incoming particles before they reach the storm's altitude. For solar wind to directly affect the Great Red Spot, it would need to bypass these defenses, perhaps through cracks in the magnetosphere or along magnetic field lines that funnel energy straight into the storm. Some researchers point to Juno's data, which shows occasional magnetic reconnection events where Jupiter's field lines snap and reconfigure, opening temporary gates for solar particles. If one of these events coincided with a solar wind surge, it could have delivered a pulse of energy right to the spot's doorstep. But here's where it gets even stranger. The solar wind doesn't just carry particles, it carries magnetic signatures from the sun itself. When the storm's new shape appeared, it didn't just resemble any random squiggle, it mirrored the twisting arcs of solar prominences. Could Jupiter's atmosphere have briefly locked onto the sun's magnetic patterns like a cosmic echo? Lab experiments with plasma, the same superheated, charged gas found in both solar flares and Jupiter's upper atmosphere, show that under the right conditions, magnetic structures can replicate across vast distances. It's a long shot, but if true, it would mean the Great Red Spot didn't just change, it momentarily danced to the sun's tune. Of course, correlation isn't causation. While the solar wind spike and the spot's transformation happened close together, proving a direct link requires more evidence. That's where future missions come in. Upcoming probes like the European Space Agency's JUICE will carry instruments designed to track how solar wind energy filters through Jupiter's atmosphere, potentially catching the next shape shift in action. Until then, the idea remains a tantalizing what if a reminder that in our solar system, even a storm a billion miles from the sun might still feel its touch. The Great Red Spot isn't just changing overnight. It's been rewriting its own story for centuries. Early astronomers sketching Jupiter through crude telescopes in the 1600s saw a sprawling oval 3 times wider than Earth. Fast forward to today, and that same storm could barely fit 2 of our planets side by side. This slow but steady shrinkage isn't just interesting trivia. It's a cosmic mystery playing out in ultra-slow motion. Modern measurements show the spot losing about 900 miles of width every Earth year, like a cosmic balloon with an invisible leak. But here's the twist: as it gets smaller, it's also growing taller, stretching vertically like taffy being pulled from both ends. Color tells another piece of the story. 19th century observers described the storm as a vivid brick red, so intense some thought it might be glowing. Today's telescopes show a paler, salmon-colored disk that occasionally darkens to orange. These shifts aren't just aesthetic changes, they're chemical fingerprints. As the storm contracts, its swirling gases may be concentrating certain compounds, altering how sunlight interacts with ammonia crystals and sulfur molecules high in Jupiter's atmosphere. Some researchers believe the spot's changing hues reflect deeper transformations, like a planetary mood ring revealing shifts in temperature and composition we can't directly observe. Then there's the speed. Historical records from the 1800s suggest the spot once raced around Jupiter faster than it does today, completing circuits in about 4 days compared to its current 6. This slowdown hints at fundamental changes in the storm's energy dynamics, like an aging athlete losing stamina but developing new techniques to stay competitive. The recent shape shift might be part of this long-term adaptation, a desperate bid to maintain stability as the storm's environment transforms around it. What's causing this centuries-long metamorphosis? One theory points to Jupiter's shifting jet streams, those raging rivers of gas that frame the storm. As these winds accelerate or change course over decades, they could be gradually strangling the spot, constricting its energy supply like a kink in a garden hose. Alternatively, the storm might be starving as Jupiter's internal heat distribution changes, depriving it of the rising warm gases that have fueled its fury for generations. The most haunting question isn't about the past, it's about the future. If current trends continue, some models suggest the Great Red Spot could become circular within 40 years, then potentially dissipate entirely. But Jupiter loves to defy predictions. In 2018, the storm suddenly intensified, spinning faster and growing slightly larger for the first time in recorded history, proof that this ancient tempest still has surprises up its sleeve. Whether it's dying or just evolving into something new remains one of planetary science's greatest cliffhangers. Jupiter's jet streams are the invisible architects of its chaotic skies, supercharged rivers of gas that make Earth's fastest winds seem sluggish by comparison. These atmospheric highways don't just breeze along at a few hundred miles per hour. They scream across the planet at speeds that would rip apart anything in their path, some exceeding 400 miles per hour. Unlike Earth's relatively orderly jet streams, which flow mostly west to east, Jupiter's weave a tangled web, with adjacent bands often racing in opposite directions. It's like having a dozen interstate highways stacked atop one another, all moving at different speeds and directions, a recipe for constant planet-wide turbulence. The Great Red Spot sits wedged between two of these raging torrents, one blasting eastward, the other hurtling westward. This precarious position turns the storm into a spinning pivot point, constantly buffeted by winds that could shred lesser vortices. Recent observations suggest something shifted in this delicate balance just before the spot's dramatic shape change. Infrared scans revealed subtle speed increases in the eastward jet, as if someone had slammed their foot on a cosmic accelerator. The added force might have stretched the storm's outer edges thin, triggering those filament-like tendrils that made it resemble a solar flare. But here's where it gets even wilder. Jupiter's jet streams aren't shallow surface features, they plunge hundreds of miles deep, according to data from NASA's Juno spacecraft. This depth means they're not just pushing storms around, they're potentially feeding them with heat and gases from Jupiter's scorching interior. Imagine a storm drawing energy not just from the winds around it, but from a pipeline stretching into unimaginable pressures below. When these deep currents fluctuate, perhaps due to internal heat waves or magnetic shifts, the effects ripple upward, altering the jet stream's behavior and, by extension, the storms they govern. The most fascinating part, these jet streams might be self-sustaining. On Earth, our jet streams rely on temperature differences between poles and equator. Jupiter's seem to generate their own energy through mechanisms we're still unraveling, possibly involving the planet's fierce rotation, internal heat, or even electromagnetic effects from its core. Some computer simulations show that once Jupiter's jets form, they create feedback loops that reinforce their own existence, like a perpetual motion machine made of gas. This could explain why the spot has persisted for centuries despite constant shear forces that should have torn it apart. The very jets that threaten it might also be supplying just enough energy to keep it alive. Yet for all their power, these atmospheric rivers aren't immutable. Historical records show Jupiter's banded cloud patterns shifting over decades, suggesting the jet streams themselves evolve. When they do, the storms caught in their flow must adapt or perish. The Great Red Spot's recent transformation might be its latest survival tactic, a reshaping forced upon it by changes in these invisible interplanetary highways. As we watch this ancient storm contort itself to ride Jupiter's shifting winds, we're witnessing more than just weather. We're seeing a masterclass in cosmic adaptation, where even the mightiest tempests must bow to the currents that shape their world. Vortex dynamics on Jupiter operate like a cosmic ballet, spinning storms pirouetting around one another in an intricate dance governed by fluid mechanics on a planetary scale. The Great Red Spot isn't the only performer on this stage. Dozens of smaller vortices whirl through Jupiter's cloud belts, some barely larger than Earth's hurricanes, others spanning continents. These storms don't just coexist, they collide, merge, and occasionally tear each other apart, creating a constantly shifting mosaic of atmospheric chaos. Take the case of Oval BA, a white storm that spent decades circling the Great Red Spot like a boxer looking for an opening. In 2018, telescopes caught it making its move, swinging close enough to the spot that their outer wind bands began intertwining. For weeks, the two storms stretched toward each other, filaments of gas bridging the gap like celestial taffy. Then, something unexpected happened. Rather than merging or annihilating each other, they settled into a delicate gravitational waltz, orbiting a shared center of mass while maintaining their individual identities. This phenomenon, called vortex pairing, reveals how Jupiter's storms can interact without destroying one another, a fragile equilibrium of push and pull that keeps the atmosphere in constant flux. But not all encounters end so peacefully. Smaller vortices often meet a far more violent fate when they approach the Great Red Spot. High-resolution images from the Hubble Space Telescope have captured the moment when storms half Earth size are shredded into ribbons by the spot's outer winds, their swirling structures unraveling like yarn caught in a spinning blade. These collisions aren't just spectacular to watch, their feeding frenzies. As the spot consumes these smaller storms, it absorbs their angular momentum, effectively stealing their spin to sustain its own rotation. It's a brutal but efficient survival strategy. In Jupiter's skies, big storms eat little ones. The physics behind these interactions hinges on something called the inverse energy cascade, a counterintuitive phenomenon where turbulence in Jupiter's atmosphere behaves opposite to how it does on Earth. Here, large storms dissipate into smaller eddies, losing energy to friction. On Jupiter, smaller vortices actually combine to fuel larger ones, channeling energy upward in scale rather than downward. This explains why Jupiter's storms grow instead of fade, and why the Great Red Spot has endured while countless smaller vortices come and go. The spot isn't just a passive beneficiary of this process. It actively shapes its environment, shepherding smaller storms into its gravitational influence like a celestial sheepdog corralling its flock. Yet even the mightiest vortex has vulnerabilities. Computer simulations show that under the right conditions, a carefully timed collision with multiple smaller storms could destabilize the Great Red Spot's delicate balance. If several vortices struck simultaneously from different angles, their combined torque might disrupt the spot's rotation, potentially triggering those sudden shape changes we've observed. Alternatively, a particularly massive storm, like the rare supervortex spotted in 2020, could transfer enough energy to deform the spot's structure without being consumed itself. What makes these dynamics so fascinating is their universality. The same principles governing Jupiter's vortices appear in Earth's oceans, in plasma fusion reactors, even in the spiral arms of galaxies. By studying how the Great Red Spot interacts with its smaller cousins, we're not just decoding Jupiter's weather, we're uncovering fundamental truths about how spinning structures behave everywhere in the universe, from the smallest whirlpool to the largest cosmic storm. Ammonia isn't just a household cleaner. It's the lifeblood of Jupiter's storms, a swirling chemical tapestry that paints the planet's skies in shades of white and ochre. High above the Great Red Spot, ammonia crystals form feathery clouds, their icy particles catching sunlight like cosmic diamonds. But these aren't just pretty decorations, they're active players in the planet's weather machine. When ammonia vapor rises from Jupiter's depths, it freezes into tiny crystals at altitudes where temperatures plunge to -150 degrees Celsius. These crystals cluster into towering thunderheads, some stretching 30 miles high, 3 times taller than Everest, and their movements might hold the key to the spot's sudden shape-shifting antics. Recent observations reveal something peculiar. The Great Red Spot's most dramatic transformations often coincide with fluctuations in ammonia concentrations around it. Spectrographs from the Gemini Observatory show plumes of ammonia-rich gas spiraling into the storm's heart just before its edges fray into those solar flare-like tendrils. It's as if the storm is gulping down chemical fuel, and the surge alters its very structure. Lab experiments back this up. When ammonia and water vapor mix under Jupiter-like pressures, they form exotic compounds that can suddenly change viscosity, like honey flipping between thick and thin. If similar shifts happen inside the spot, they could explain why parts of the storm stiffen or loosen overnight, reshaping its silhouette like putty in invisible hands. But ammonia's role goes beyond mere chemistry. These clouds act as atmospheric flywheels, storing and releasing energy in ways we're only beginning to understand. Infrared scans from NASA Juno spacecraft reveal hotspots where ammonia clouds seem to be collapsing, dumping their latent heat into the storm below like batteries discharging. Other regions show the opposite: ammonia freezing midair, sucking warmth from the surrounding gases. This push and pull could create the turbulence needed to twist the spot's outer layers into those bizarre filaments. Imagine a pot of soup boiling unevenly. Some spots bubble violently while others stay eerily calm, creating a chaotic dance of rising and sinking currents. Now scale that up to a storm wider than planets, and you've got Jupiter's ammonia-driven weather engine. The strangest twist: ammonia might be painting the storm's iconic color. For decades, scientists assumed sulfur compounds alone tinted the spot crimson. But lab simulations show that when ammonia interacts with acetylene, a gas abundant in Jupiter's upper atmosphere under ultraviolet light, it can produce reddish-brown polymers. If the spot's ammonia clouds are deeper or shallower during transformations, they could be filtering sunlight differently, explaining why the storm darkens or pales when it morphs. It's a cosmic mood ring, with ammonia playing chemist and artist simultaneously. Yet mysteries remain. Some ammonia plumes dive straight into the spot's core, while others skirt its edges like shy spectators. Computer models suggest these delivery routes matter. Storms fed by deep, direct ammonia injections might grow more stable, while those nibbling at the fringes could destabilize faster. This could explain why the spot's changes seem so erratic. It's not just about how much ammonia is present, but where and how it enters the storm's endless whirl. Every time we peer into Jupiter's churning skies, we're reminded that even the simplest molecules can orchestrate the grandest cosmic performances when the stage is a planet where chemistry and chaos waltz together. Planetary waves roll through Jupiter's atmosphere like invisible tsunamis, vast, slow-moving ripples that can stretch thousands of miles across the gas giant's cloud tops. Unlike the violent jet streams that carve the planet's colorful bands, these waves operate on a subtler scale, nudging storms and altering wind patterns with the quiet persistence of a cosmic heartbeat. Scientists believe these hidden disturbances might be the puppeteers behind the Great Red Spot's sudden shape shifting, warping its edges with forces too gradual to see in real time but powerful enough to rewrite the storm's structure overnight. What makes planetary waves so fascinating is how they travel. Picture dropping a pebble into a pond. The ripples spread outward in perfect circles. On Jupiter, the physics are similar, but the pebble might be a massive storm eruption, and the pond is an ocean of hydrogen and helium thousands of miles deep. These waves don't just move horizontally, they propagate vertically too, tunneling energy between different layers of Jupiter's atmosphere like whispers passing through a labyrinth. Some waves take months to cross the planet, their crests and troughs subtly bending wind currents as they pass. Others oscillate up and down, transferring heat from the scorching depths to the frigid cloud tops, creating pockets of instability where storms like the Great Red Spot become vulnerable to sudden change. Detecting these waves isn't as simple as pointing a telescope. Their effects are often buried in noise, masked by Jupiter's more dramatic weather features. It took a combination of NASA, a Juno spacecraft, and Earth-based observatories to spot the telltale signs patterns of alternating temperature and wind speed that couldn't be explained by jet streams alone. In 2021, researchers analyzing Juno's microwave data noticed something peculiar: rhythmic fluctuations in atmospheric pressure near the Great Red Spot, like the rise and fall of tides. These weren't random blips, they matched the predicted behavior of planetary waves, their timing aligning eerily with periods when the spot's shape began to distort. The real breakthrough came when scientists fed these wave patterns into supercomputer simulations. The models showed something startling. When certain planetary waves converged on the Great Red Spot, their combined energy could stretch the storm's outer edges, thinning its swirling gases until they peeled away like layers of an onion. This wasn't a brute force collision, it was a resonance effect, where wave frequencies matched the spot's natural vibrational modes, amplifying their impact like a singer shattering glass with the right note. The simulations even recreated those solar flare-like filaments Hubble observed, suggesting waves might be the invisible sculptors behind the storm's most dramatic transformations. Yet planetary waves don't act alone. Their influence depends on Jupiter's deeper atmospheric orchestra, the jet streams that steer them, the magnetic fields that may channel their energy, and even the planet's own rotation, which twists their paths into spirals. Some researchers speculate these waves could be delivering energy from Jupiter's hidden interior, acting as conveyor belts for the heat and turbulence that keep storms alive. Others think they might trigger chain reactions, destabilizing one region of the atmosphere and sending shockwaves through adjacent systems. The more we learn, the clearer it becomes. Jupiter's weather isn't just about what we see on the surface. Planetary waves are the unseen architects of its chaos, the quiet forces that shape storms across centuries, and sometimes in just one night. Every time the Great Red Spot twists into a new form, it might be responding to rhythms we're only beginning to hear, echoes of a planetary symphony playing deep beneath the clouds. Saturn's storms rage with a ferocity that would dwarf Earth's worst hurricanes, yet they flicker out in years, not centuries. Neptune boasts the fastest winds in the solar system, screaming at over 1,000 miles per hour, but its great dark spot vanished within 5 years of discovery. Even Uranus, tilted on its side like a cosmic bowling ball, churns with tempests that come and go like passing seasons. So why does Jupiter's Great Red Spot outlast them all? The answer lies in the hidden machinery of these gas giants, where subtle differences in composition, rotation, and energy create weather systems as unique as fingerprints. Take Saturn's hexagonal storm, a six-sided jet stream swirling around its north pole like a colossal honeycomb. This geometric oddity has persisted for at least 4 decades, yet it lacks the depth and thermal intensity of Jupiter's Great Red Spot. NASA Cassini probe revealed Saturn's storms draw energy from seasonal sunlight, making them prisoners of the planet's 30-year orbit. When winter comes, some storms simply starve. Jupiter, by contrast, generates its own heat from within, radiating nearly twice the energy it receives from the sun, a built-in furnace that keeps its storms churning regardless of sunlight. Neptune's Great Dark Spot tells another story. Discovered by Voyager 2 in 1989, This Earth-sized vortex vanished by 1994, only to be replaced by a new storm in the northern hemisphere. Hubble later spotted another dark spot forming and dissipating within years. The difference: Neptune's storms seem to be skin-deep, lacking the deep roots that anchor Jupiter's great red spot. Juno's microwave scans show the spot plunging over 200 miles into Jupiter's atmosphere, a depth that stabilizes it against disruptions. Neptune's winds may be faster, but without this vertical structure, its storms are like fireworks, brilliant but fleeting. Then there's Uranus, where storms erupt unpredictably, possibly fueled by methane condensation or internal heat bleeding through its icy mantle. Unlike Jupiter's orderly banded clouds, Uranus' atmosphere resembles a frosted window pane struck by hail, chaotic splotches appearing and fading without pattern. The key difference: rotation. Jupiter's 10-hour day whips its atmosphere into a frenzy, organizing storms into stable lanes like cars on a racetrack. Uranus' sluggish 17-hour spin and extreme axial tilt creates a turbulent free-for-all where storms struggle to find equilibrium. Yet the most telling clue comes from chemistry. Saturn and Neptune storms are rich in methane, while Jupiter's great red spot brims with ammonia and sulfur compounds. These substances don't just color the storms, they change how energy flows through them. Ammonia's ability to freeze, thaw, and form complex polymers might give Jupiter's storms a self-reinforcing structure that methane-heavy storms lack. Laboratory experiments show ammonia clouds under Jupiter-like conditions can form stable, layered vortices, something methane struggles to replicate. The deeper lesson: storms aren't just weather, they're expressions of a planet's soul. Jupiter's internal heat, rapid spin, and chemical brew conspire to create storms that behave like living entities, adapting and enduring. Other gas giants offer snapshots of what happens when even one ingredient changes. Slower rotation turns storms chaotic, seasonal light leaves them vulnerable, and different chemistry makes them ephemeral. By studying this cosmic menagerie, we're not just solving the riddle of the great red spot's longevity, we're uncovering the universal laws that govern atmospheres across the galaxy, from Saturn's hexagon to the hurricane-racked exoplanets orbiting distant stars. While professional astronomers peer at Jupiter through billion-dollar telescopes, some of the most groundbreaking observations come from backyard stargazers armed with nothing more than passion and consumer-grade equipment. Across the globe, amateur astronomers train their lenses on Jupiter's swirling face, capturing high-resolution images that rival those from early space probes. These citizen scientists don't just take pretty pictures, they're frontline witnesses to the gas giant's ever-changing storms, often spotting anomalies long before the professionals do. When the Great Red Spot began its bizarre shape-shifting act, it was an amateur in Texas who first noticed the fraying edges, alerting researchers to the unfolding drama. What makes these observations so valuable? Consistency. Major telescopes like Hubble can't monitor Jupiter around-the-clock. Observation time is precious and shared among countless research projects. Amateurs fill the gaps, keeping near constant vigil as the planet rotates. Some devote entire nights to imaging Jupiter's storms, stacking thousands of frames to cut through Earth's atmospheric blur. The result: time-lapse sequences showing storms evolving in real time, revealing details even spacecraft miss. In 2020, a Japanese hobbyist's footage caught a rarely seen phenomenon: small vortices merging near the spot's edge, a process scientists had only simulated until then. The collaboration between professionals and amateurs has birthed formal programs like NAS, a Jovian Vortex Hunter, where volunteers analyze images to identify storm interactions. One participant in Portugal spotted a mysterious dark streak near the Great Red Spot that turned out to be an atmospheric wave distorting cloud layers, a discovery that made its way into a peer-reviewed paper. Others track subtle color changes in the spot's clouds, providing clues about chemical shifts that might precede structural transformations. Technology has erased the line between amateur and professional capabilities. Modern 8-inch telescopes equipped with planetary cameras can resolve features as small as 300 miles across, enough to see storms the size of Texas brewing in Jupiter's belts. Free software like WinJupos lets enthusiasts precisely measure wind speeds by tracking cloud features across successive images. Some amateurs even contribute to radio astronomy, tuning into Jupiter's natural radio emissions to monitor magnetic activity that influences storms. The most exciting part, these observations aren't just supporting science, they're driving it. When dozens of amateurs across different continents reported the spot darkening in 2022, it prompted professional observatories to investigate, leading to the discovery of a previously unnoticed ammonia upwelling event. In another case, coordinated observations by amateur networks helped pinpoint the exact moment a jet stream accelerated near the spot, providing critical data for computer models. This isn't just about filling data gaps, it's about fostering a global community united by cosmic curiosity. From retirees in Arizona tracking atmospheric waves to students in Chile measuring the spot's rotation speed, these citizen scientists prove you don't need a PhD to advance our understanding of the solar system. Every time someone points a telescope at Jupiter and notices something odd, they're participating in a tradition that dates back to Galileo, pushing the boundaries of human knowledge one observation at a time. The next chapter in Jupiter's exploration is already unfolding, with spacecraft like the European Space Agency's JUICE, the Jupiter Icy Moons Explorer, poised to revolutionize our understanding of the gas giant and its turbulent skies. Slated to arrive in 2031 after a nail-biting 8-year journey, JUICE won't just gaze at Jupiter from afar. It'll dive into the planet's gravitational and magnetic fields, mapping hidden currents that might hold the keys to the Great Red Spot's endurance. Armed with an ice-penetrating radar and sensors capable of sniffing out trace atmospheric chemicals, this mission could finally reveal whether the spot's roots plunge deeper than we've ever imagined, perhaps tapping into energy reservoirs far below the visible cloud tops. But JUICE isn't traveling alone. NASA Europa Clipper, launching later this decade, will perform daring flybys of Jupiter itself between studies of its icy moon. These close passes offer a golden opportunity to measure the planet's atmospheric waves in unprecedented detail, the same waves that might have triggered the spot's sudden shape shifts. Imagine high-resolution sensors catching the moment a planetary wave collides with a storm, documenting how its structure trembles in response, even more tantalizing. Both missions carry instruments to monitor Jupiter's magnetosphere in real time, letting scientists test once and for all whether solar wind surges or magnetic anomalies are puppeteering the spot's transformations. The real game-changer might come from an unexpected direction. JUICE extended focus on Jupiter's moons. Ganymede's magnetic field interacts violently with Jupiter's own, creating electromagnetic feedback loops that ripple through the planet's atmosphere. By studying these interactions, researchers hope to uncover whether moon-induced magnetic tremors could be jostling the Great Red Spot from afar, a celestial domino effect where events 500,000 miles away reshape the solar system's largest storm. Meanwhile, here on Earth, a new generation of telescopes is joining the hunt. The extremely large telescope, set to see first light in 2028, will image Jupiter's storms with resolutions previously possible only from space, tracking minute-by-minute changes in the spot's chemistry and temperature. Combined with data from the James Webb Space Telescope's infrared eyes, astronomers might catch the storm mid-metamorphosis, watching how its heat signature shifts seconds before its shape contorts. Yet the most exciting prospects lie beyond hardware. Machine learning algorithms are now sifting through centuries of Jupiter observations, from Galileo's hand-drawn sketches to Juno's terabytes of data, to uncovering patterns no human could spot. Early results suggest the Great Red Spot's transformations might follow a hidden cycle, with subtle clues appearing months in advance. Future missions could use these AI predictions to position spacecraft at the perfect angle, cameras ready, the next time the storm decides to rewrite its own rulebook. What makes this era different isn't just better technology, it's coordination. For the first time, orbiters, ground-based telescopes, and amateur networks will observe Jupiter in unison, creating a multidimensional portrait of its storms. When the next big change shakes the Great Red Spot, we won't just see it from one vantage point. We'll have probes measuring magnetic pulses, telescopes analyzing chemical fingerprints, and citizen scientists capturing time lapses, all synced to the same cosmic moment. This collaborative approach turns Jupiter into a living laboratory, where every storm, every wave, every flicker of light becomes a piece of a puzzle we're finally equipped to solve. The ultimate goal isn't just to explain why the spot changes shape, but to predict it, to move from reactive observation to proactive forecasting. If we can decode the storm's behavior, the same principles might apply to turbulent atmospheres light years away, on exoplanets where storms rage for millennia under alien suns. Jupiter's greatest gift could be proving that even the most chaotic systems follow rules. We just need the right tools, the right missions, and enough patience to listen to what the storm has been trying to tell us all along. Jupiter's storms aren't just a spectacle in our solar system. They're a Rosetta Stone for decoding the violent weather raging on exoplanets light years away. Imagine a gas giant 5 times Jupiter's size, orbiting perilously close to its star, where temperatures soar high enough to vaporize iron. Telescopes can't yet see the details of its atmosphere, but thanks to Jupiter, we can make an educated guess. That planet is likely a maelstrom of superheated storms, banded jet streams, and vortices that dwarf even the Great Red Spot. The physics governing Jupiter's chaos, fluid dynamics, heat transfer, and magnetic interactions aren't unique to our neighborhood. They're universal laws playing out on a cosmic stage, and every twist in the Great Red Spot's behavior hints at what might be happening in atmospheres we can barely detect. Consider hot Jupiters, a class of exoplanets so close to their stars they're literally roasting. Before studying Jupiter, astronomers assumed these worlds might have bland, featureless atmospheres, too hot for complex weather. But infrared observations reveal something startling. Many show temperature variations suggesting massive storm systems. Some even exhibit day-night temperature differences of thousands of degrees, likely driving winds that would make Jupiter's 400-mile-per-hour gales feel like a breeze. The Great Red Spot's ability to thrive on internal heat, not just sunlight, suggests these distant storms might be even more violent and long-lived than we imagined. If Jupiter's storms tap into energy from deep within the planet, a hot Jupiter's internal furnace, heated by tidal forces from its star, could birth hurricanes that last millennia. Then there's the mystery of puffy exoplanets, gas giants with densities so low they resemble cotton candy. Their extreme fluffiness might come from intense internal heating, much like Jupiter's own heat surplus. If these worlds churn with similar energy, their storms could behave in bizarre, counterintuitive ways. Computer models based on Jupiter's atmospheric data suggest some puffy planets might host storms that rise like thermal balloons, expanding until they engulf entire hemispheres before collapsing. a cycle repeating every few years. Others could develop permanent storm systems locked at their poles, like Saturn's hexagon, but on a scale that defies imagination. The real breakthrough lies in magnetic fields. Jupiter's magnetic fury shapes its storms in ways we're only beginning to understand, and exoplanet hunters have spotted gas giants with magnetospheres hundreds of times stronger. On these worlds, storms might not just be shaped by wind and heat, they could be threaded with electric currents, glowing like neon signs in the cosmic dark. Some researchers speculate that certain exoplanet auroras, detected by their radio emissions, might actually be the signatures of storms crackling with electromagnetic energy, their outer edges fraying into tendrils just like the great red spot's solar flare-like filaments. But the most profound implication isn't about gas giants alone. Jupiter's storms teach us that atmospheric behavior follows universal fluid dynamics, whether on a planet, a star, or even in the swirling disks where new worlds form. When we see a distant exoplanet's atmosphere dimming unpredictably, a sign of towering clouds or violent storms, we're essentially reading a weather report written in a language Jupiter helped us decipher. The Great Red Spot's transformations aren't just a curiosity, they're a masterclass in how chaos organizes itself across the universe, one that's preparing us to interpret the first direct images of exoplanet skies. Every time this ancient storm surprises us, it's not just rewriting Jupiter's story, it's giving us the vocabulary to understand worlds we've yet to name. When those first images of the Great Red Spot's distorted shape hit scientific journals and social media feeds, the reaction was electric. Amateur astronomy forums lit up with side-by-side comparisons, Reddit threads dissected every pixel, and even mainstream news outlets ran headlines about Jupiter's cosmic makeover. There's something primal about our fascination with this distant storm. Maybe it's the sheer scale, a tempest so vast our entire planet could vanish inside it. Or perhaps it's the haunting realization that even after centuries of observation, the universe still holds surprises that defy our expectations. The storm's transformation tapped into a deeper curiosity about worlds beyond our own. Unlike Earth's weather, which follows patterns we can predict days in advance, Jupiter's atmosphere operates by rules that feel almost alien. Its storms don't just come and go, they evolve, merge, and sometimes rewrite their own identities overnight. This unpredictability mirrors our own complex relationship with nature's chaos. We watch tornadoes form and dissipate in minutes, but Jupiter offers a slow-motion spectacle where atmospheric drama unfolds over lifetimes, inviting us to ponder time itself on a planetary scale. Social media played an unexpected role in decoding the event. When professional observatories released raw data, citizen scientists jumped in, enhancing images and tracking subtle changes missed by algorithms. One viral TikTok even overlaid the storm's new shape with footage of solar flares, a visual comparison that caught the attention of researchers. This collaborative excitement underscores how space exploration has shifted from the domain of elite institutions to a shared human experience, where anyone with curiosity can contribute to the story. Yet the fascination isn't just scientific, it's philosophical. The Great Red Spot's endurance and its sudden changes forces us to confront how little we truly understand about longevity in the cosmos. Here's a storm that predates the steam engine, the light bulb, the internet, yet it's still reinventing itself. In an era of climate change and ecological fragility, Jupiter's tempest feels like a distant cousin to Earth's own turbulent systems, whispering reminders about resilience, adaptation, and the raw power of natural forces we'll never fully control. Artists and writers seized the moment too. Digital illustrators reimagined the storm as a living entity, its new tendrils like grasping fingers. Sci-fi authors spun tales of alien weather engineers tampering with Jupiter's skies. Even musicians composed eerie, atmospheric tracks inspired by the event, sonifying data from the storm's wind speeds into haunting melodies. This cultural response proves that planetary science isn't just about data, it's a canvas for humanity's imagination, a mirror reflecting our awe of the unknown. What makes this public reaction truly remarkable is its contrast to how we perceive other celestial events. A supernova dazzles us with its brilliance, a black hole unnerves us with its mystery, but Jupiter's weather feels strangely familiar, almost relatable. It's a storm just like ones we experience on Earth, but amplified to a scale that bends comprehension. That duality, the recognizable made alien, hooks us. We see our own world storms in Jupiter's chaos, and yet we're reminded that the universe operates on terms far beyond human intuition. The Great Red Spot didn't just change shape, it reshaped how we see our place in a cosmos where even the oldest, most studied phenomena can still startle us into wonder. The Great Red Spot has sparked wild theories ever since humans first pointed telescopes at Jupiter. Some claim it's a portal to another dimension. Others insist it's evidence of alien technology manipulating the planet's atmosphere. Even predictions linking its changes to apocalyptic events on Earth have surfaced online. But let's step back from science fiction and examine what we actually know about this swirling enigma. First, the idea that the spot is artificially created collapses under basic physics. This storm isn't some floating structure. It behaves exactly like a natural vortex, just on a planetary scale. The same fluid dynamics that govern whirlpools in your bathtub apply here, amplified by Jupiter's lack of a solid surface and its insane rotational speed. When simulations can recreate the spot's behavior using equations derived from earthly weather patterns, extraterrestrial engineering becomes an unnecessary complication. Then there's the myth that the storm's color changes signal impending catastrophe. Yes, the spot has darkened and lightened over the centuries, but lab experiments show this is easily explained by chemistry, not omens. When ultraviolet light hits ammonia and sulfur compounds in Jupiter's upper atmosphere, it triggers reactions that produce reddish polymers. Variations in cloud depth or solar exposure would naturally alter this coloration without invoking supernatural forces. Even the recent shape shift aligns perfectly with known wind shear phenomena. We've watched smaller Jovian storms distort similarly for decades. Perhaps the most persistent fiction is that Jupiter's storms influence Earth. While the gas giant's gravity does affect asteroid orbits, its atmospheric turbulence has zero connection to our weather or seismic activity. The planets are simply too far apart. At their closest, Jupiter is still over 365 million miles away. That's like claiming a breeze in Tokyo could extinguish a candle in New York. The real wonder isn't fabricated mysteries, it's how nature crafts such complexity without any hidden hand. The Great Red Spot's endurance comes from Jupiter's internal heat, its rapid spin, and deep-rooted atmospheric currents, not alien intervention, those bizarre solar flare-like filaments. They're textbook examples of how fluids behave under extreme shear forces, visible in plasma physics experiments right here on Earth. What makes debunking these myths important isn't just setting the record straight, it's highlighting how much more fascinating reality is than fiction. The truth that a self-sustaining vortex can churn for centuries, governed by universal physical laws, challenges our imagination far more than any conspiracy theory. Jupiter doesn't need artificial explanations to be awe-inspiring. Its natural chaos is spectacular enough. Jupiter's swirling storms aren't just celestial spectacles, they're masterclasses in physics, offering educators a dynamic way to bring complex scientific principles to life. Picture a high school classroom where students typically yawn through fluid dynamics equations, but their eyes light up when you project a time lapse of the great red spot morphing overnight. Suddenly, abstract concepts like wind shear and vortex stability snap into focus. The spot's transformation becomes more than a distant curiosity. It's a real-world lab where the laws of motion, thermodynamics, and electromagnetism collide on a planetary scale. Take fluid dynamics, a topic that often feels trapped in textbooks. Jupiter's atmosphere demonstrates these principles with cinematic flair. Teachers can contrast Earth's short-lived hurricanes, which fade without warm ocean water, with Jupiter's self-sustaining storms, fueled by internal heat and unhindered by land. Students can map the Great Red Spot's rotation against equations predicting vortex behavior, then debate why it defies expectations by lasting centuries. Hands-on activities deepen the lesson, swirling colored water in tanks to simulate jet streams, or using computer models to tweak variables like wind speed and watch virtual storms evolve in real time. These experiments don't just teach science, they reveal how universal these laws are, governing everything from bathtub drains to galactic nebulae. Meteorology lessons leap off the page when Jupiter enters the mix. Comparing Earth's weather to Jupiter's extreme climate highlights the role of planetary ingredients. Why does Jupiter have banded clouds and storms that never cross the equator? A simple demo with rotating globes and layered fluids, oil for gas giants, water for Earth, shows how differing rotation speeds and atmospheric compositions create wildly different weather patterns. Even younger students grasp why Jupiter's storms dwarf ours when they learn its fastest winds could cross the United States in under an hour. Astronomy education transforms when students analyze Hubble images to track the spot's changes, calculating its shrinking size or predicting its next color shift. Citizen science projects let classrooms contribute data to professional studies, like measuring wind speeds from amateur telescope photos. One school in Colorado collaborated with a local university to document a smaller storm merging with the spot, their findings later cited in a research paper. These experiences don't just teach, they ignite careers. The Great Red Spot's recent shape-shifting offers a golden opportunity to discuss the scientific method. Students can dissect how researchers test hypotheses. Did solar wind trigger the change, a hidden heat surge, and why multiple explanations might coexist? Debates erupt over which evidence matters most: thermal scans, magnetic readings, or chemical analyses. This mirrors real science, where answers are often messy and evolving. Beyond physics, Jupiter's storms bridge disciplines. Chemistry classes explore how ammonia and sulfur create the spot's hues, while math students model its fractal-like edges using geometry. Art students even sketch its evolving forms, observing how nature blends chaos and symmetry. The ultimate lesson: science isn't a series of isolated facts, it's a living, interconnected story, and Jupiter's tempests are one of its most thrilling chapters. Educators worldwide are tapping into this potential. In Australia, a teacher built a Jupiter weather station, where students simulate atmospheric layers with heated fluids and dyes, watching storms form as temperatures shift. A Canadian school partnered with a radio observatory to track Jupiter's magnetosphere, linking magnetic pulses to storm activity. These projects prove that when science feels immediate and immense, when a student realizes the equations they're solving govern a storm wider than their planet, it sparks a curiosity no textbook can match. The Great Red Spot's magic lies in its ability to make the unimaginable tangible. A child who struggles to picture fluid dynamics can instantly grasp the concept when they see a storm older than their country twisting into a new shape. It's a reminder that the universe isn't just a collection of distant objects, it's a classroom without walls, where every swirling cloud tells a story about the forces shaping our world and beyond. Artistic visions of Jupiter's storms have always walked the line between awe and accuracy, a dance of imagination and scientific rigor that shapes how we see the cosmos. When filmmakers depict the Great Red Spot as a swirling crimson abyss in sci-fi epics, or when digital artists render its turbulent edges with dreamlike precision, they're not just creating eye candy, they're translating raw data into emotional experiences. Take the iconic sequences from documentaries like Cosmos or Jupiter, the giant planet where CGI storms pulse with lightning and towers of ammonia clouds rise like skyscrapers. These visuals aren't mere speculation, they're often built pixel by pixel from NASA probe imagery, yet amplified to stir wonder. The result, a public that doesn't just know Jupiter is stormy, they feel its tempests in their bones. But artistic license can cut both ways. Blockbusters sometimes exaggerate the spot's scale or stability for dramatic effect, leaving audiences surprised when real telescope footage shows a more nuanced reality. Remember the Vortex in 2010, the year we make contact, portrayed as a gateway to alien contact. While thrilling, it fueled myths about the storm's unnatural origins. Yet even these embellishments serve a purpose. They spark curiosity. A teenager watching a fictionalized Jupiter storm might later seek out raw Juno mission footage, launching a lifelong passion for planetary science. The most compelling interpretations blend art and academia. Icelandic composer Jónsi created a symphonic piece using day to sonification, translating the Great Red Spot's wind speeds into eerie, undulating melodies. Meanwhile, digital painters like Michael Benson stitched together thousands of probe photos into hyper-detailed panoramas, revealing textures and hues invisible to the naked eye. These works don't just reflect science, they advance it. Benson's composites have actually helped researchers spot subtle atmospheric changes, proving art can be a tool of discovery. Perhaps the deepest impact lies in accessibility. Scientific papers describe the spot's shear forces with equations, but a kinetic sculpture, like Luke Jerram's swirling glass installation Jupiter Storm, makes those forces tactile. When a museum visitor sees light fracture through the piece's spiraling layers, they intuitively grasp concepts like fluid dynamics and vorticity without cracking a textbook. This synergy of beauty and logic demystifies the cosmos, inviting everyone, not just astrophysicists, to marvel at its complexity, the challenge for creators. Balancing spectacle with authenticity, NASA Visions of the Future poster series nails this, depicting Jupiter's storms as both surreal and scientifically grounded, with color palettes pulled directly from spectrometer readings. Similarly, the Exoplanet Travel Bureau series uses real exoplanet data to paint storms on distant worlds, subtly teaching viewers about atmospheric chemistry through artistry. These projects remind us that Jupiter's storms aren't just subjects of study, they're muses, pushing us to see science not as cold facts, but as a canvas where truth and imagination collide. Ultimately, these artistic interpretations do more than entertain. They bridge the gap between the public and the cosmos. A child who doodles Jupiter's storms after seeing a viral space illustration, a filmmaker who consults astrophysicists to perfect a storm scene. These connections weave science into culture. The Great Red Spot becomes more than a weather pattern. It's a shared symbol of nature's grandeur, reminding us that some mysteries are too vast for equations alone. They need color, sound, and story to be fully understood, or at least to be fully felt. As we marvel at Jupiter's storms from afar, a quieter question lingers. Do we have the right to interfere with worlds we don't yet understand? The gas giant's atmosphere may seem invulnerable to human meddling, a raging tempest where no probe could ever leave a mark, but history warns us against such assumptions. Every time humanity has ventured into uncharted territory, from ocean depths to rainforest canopies, we've discovered delicate balances we never knew existed. Jupiter's complex chemical cycles, its mysterious energy transfers between layers, even the great red spot's improbable longevity, these could all be part of systems far more fragile than they appear. Consider the precedent set by our own planet. When scientists first proposed releasing harmless tracer gases to study Earth's jet streams, critics warned of unintended consequences. What if those gases interacted unpredictably with ozone? Similar concerns apply to Jupiter. Future missions might deploy atmospheric drones or floating observatories, devices designed to survive its hellish winds. But even these could introduce contaminants not biological but chemical, that might subtly alter cloud formation or storm dynamics over centuries. The sheer scale of Jupiter doesn't make it immune. It just means changes would unfold on timelines longer than human lifespans, invisible until it's too late. The ethical debate intensifies when we contemplate terraforming, not of Jupiter itself but its moons. Europa's subsurface ocean and Io's volcanic plains are already prime targets for exploration. Some futurists envision melting Europa's ice to create Earth-like habitats, a process that would inevitably affect Jupiter's magnetosphere and radiation belts. These aren't abstract thought experiments. Private companies have already floated proposals to mine Jupiter's atmospheric helium-3 for fusion energy. While technically feasible, such ventures raise profound questions about our role in the solar system. Should gas giants be protected as natural laboratories, their storms and chemistry preserved like wilderness areas? Or do they represent resources for humanity's expansion, theirs to reshape as needed? International space law offers little guidance. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies but says nothing about environmental protection. Current planetary protection protocols focus solely on preventing biological contamination, ensuring we don't accidentally seed Europa with Earth microbes. There's no equivalent for preserving atmospheric or geological processes. This legal vacuum leaves scientists navigating uncharted ethical terrain. When the European Space Agency's JUICE mission arrives at Jupiter in 2031, its instruments will penetrate deeper into the planet's clouds than any probe before it. The data will be invaluable, but should there be limits to how much we disturb the very systems we seek to study? Perhaps the most compelling argument for restraint comes from Jupiter itself. The Great Red Spot's recent transformation proves we're still beginners at understanding planetary scale weather. What appears chaotic might follow rhythms we can't yet perceive. What seems eternal might be hanging by a thread. Interfering prematurely could rob future generations of insights we can't yet imagine. There's humility in acknowledging that some mysteries deserve to remain undisturbed, not because we lack the technology to probe them, but because the universe's grandeur sometimes outweighs our curiosity. Yet exploration has always carried ethical tensions. The same telescopes that reveal Jupiter's beauty also serve military satellites. The same rockets delivering probes could one day carry weapons. This duality isn't unique to space. It mirrors every technological leap in human history. The challenge isn't avoiding progress but steering it wisely. Maybe the answer lies in treating Jupiter not as a resource or a lab, but as a teacher. Its storms have weathered 4 billion years of cosmic history. They might have more to tell us if we're patient enough to listen rather than eager to alter. After all, the greatest discoveries often come not from imposing our will on nature, but from learning its language. one swirling, tempestuous word at a time. Imagine controlling Jupiter's storms with a swipe of your finger, not in a sci-fi fantasy, but through cutting-edge simulations that bring planetary science to your smartphone. Across the globe, interactive tools are transforming how we engage with Jupiter's chaotic weather, turning abstract concepts into hands-on experiences. Platforms like NASA, Eyes on the Solar System, let users zoom into the Great Red Spot, adjusting wind speeds or atmospheric layers to see how the storm reacts in real time. These aren't just pretty animations, they're powered by real data from Juno and Hubble, allowing anyone to experiment with the same variables scientists use. A high school student in Tokyo can tweak ammonia concentrations to watch the spot's color shift, while a retiree in Barcelona manipulates magnetic field strengths to see how they sculpt the storm's edges. Suddenly, the gas giant's mysteries aren't locked behind academic papers, they're playfully unraveled through trial and error. The magic lies in how these tools democratize discovery. Take the Jovian Vortex Hunter project, where amateur astronomers classify storms in Juno's raw images, contributing directly to research. One volunteer in New Zealand spotted a rare storm merger that made its way into a peer-reviewed study. Elsewhere, apps like Solar System Scope use augmented reality to superimpose Jupiter's swirling atmosphere onto your living room floor, letting you walk through jet streams like a cosmic giant. These experiences don't just teach, they spark visceral connections. When you pinch zoom into the spot's fractal-like tendrils or tilt your tablet to simulate Jupiter's rotation, the planet's scale and violence become tangible in ways textbooks can't match. But the real innovation is under the hood. Behind the sleek interfaces, these tools rely on fluid dynamics algorithms refined by supercomputers. The Jupiter Simulator from the University of Barcelona, for instance, lets users inject virtual storms into the planet's bands, then watch as the laws of physics dictate whether they grow, shrink, or collide. It's a cosmic sandbox where every experiment reveals something new, like how changing the Coriolis effect mimics storms on Saturn or Neptune. Educators have seized these resources too. In classrooms from Oslo to Sydney, students collaborate to predict the spot's next shape shift, then compare their models to actual Hubble updates. The result: a generation learning that science isn't just memorizing facts. It's about testing ideas in the universe's grandest laboratory. What's next? Emerging tech like virtual reality promises even deeper immersion. Picture strapping on a headset and standing inside the Great Red Spot's churning walls, with 360-degree visuals rendered from Juno's flyby data. Startups are already prototyping haptic gloves that let you feel the storm's turbulence through vibrations, a leap toward making planetary science as intuitive as playing a video game. Yet the true impact isn't technological, it's cultural. By shrinking the solar system to a screen, these tools remind us that Jupiter isn't just a distant dot. It's a dynamic, evolving world, and its storms, once the sole province of astronomers, now belong to anyone curious enough to explore them. The Great Red Spot's sudden shape-shifting serves as a humbling reminder. No matter how much we think we know about our cosmic neighborhood, the universe always keeps a few cards up its sleeve. This swirling tempest, older than the telescope itself, has spent centuries defying expectations, but its overnight transformation wasn't just a spectacle, it was a cosmic wake-up call. Jupiter's storms operate by rules we're still deciphering, where familiar forces like wind and heat collide with alien phenomena. Metallic hydrogen oceans, planet-sized magnetic fields, and atmospheric depths where pressure turns gas into liquid metal. Every bizarre twist in the spot's behavior, from its solar flare-like tendrils to its unexplained color shift, MORPHS is a breadcrumb leading us deeper into the labyrinth of planetary science. What makes these discoveries so exhilarating isn't just their strangeness, it's their universality. The same physics that sculpt Jupiter's storms likely governs atmospheres on distant exoplanets, where hurricanes rage under the light of alien suns. When we watch the Great Red Spot dance, we're glimpsing a choreography repeated across the cosmos, a reminder that nature's patterns transcend any single world. Missions like Juno and JUICE aren't just exploring Jupiter, they're compiling a dictionary to translate the language of gas giants everywhere. Every gravity map, every magnetic reading, every infrared scan is another syllable decoded in this interstellar dialogue. Yet for all our progress, Jupiter guards its secrets jealously. Why does the spot occasionally flare brighter before changing shape? How do its roots tap into energy sources hundreds of miles below? Even as Juno's data floods in, these questions multiply faster than answers, a testament to the gas giant's infinite complexity. But that's the thrill of exploration. The more we learn, the clearer it becomes that the universe is grander, weirder, and more wondrous than we ever imagined. The next chapter of this story is already being written. Upcoming missions will probe deeper, telescopes will capture sharper details, and citizen scientists will spot anomalies hidden in plain sight. Perhaps one day we'll witness the spot's final act, not with a dramatic collapse, but a slow fade into Jupiter's ever-churning canvas. Or maybe it will outlive us all, a perpetual monument to nature's ingenuity. Either way, its legacy is secure, a storm that taught us to expect the unexpected, to question our assumptions, and to embrace the beautiful chaos of discovery. So keep looking up, whether through a backyard telescope or a NASA live stream. Jupiter's ever-changing skies promise fresh mysteries with every orbit. The Great Red Spot's greatest lesson isn't about storms or planets, it's about curiosity itself, the unshakable human drive to peel back the universe's layers, one enigma at a time. And as long as those clouds keep swirling, the adventure is far